Hi everyone and welcome to Pharmacology. I am a board-certified, residency-trained clinical pharmacist with over 10 years of clinical practice experience. My goal is to provide the resource that I wish I had as a student and new practitioner. At pharmacology.com, you can find complete study units with charts, illustrations, and videos like these, so follow on Instagram, Pinterest, and YouTube to stay connected. In this study unit, we will be reviewing the coagulation cascade. Let's get started. Whenever there is bleeding in the body, the response is going to be the same, to stop the bleeding. And it does this by forming blood clots. This process of stopping the bleeding is called hemostasis. Hemo meaning blood and stasis meaning stop. Hemostasis is achieved in two steps, primary hemostasis and secondary hemostasis. Primary hemostasis is more of a quick fix, like a band-aid fix if you will. Primary hemostasis occurs rather quickly once there is injury to a vessel, and it consists of an aggregate of platelets that form a loose platelet plug that sticks to the injured vessel with the help of the von Willebrand factor. Secondary hemostasis, also known as the coagulation cascade, is more complex. It involves two separate pathways that feeds into a common pathway and also involves many more clotting factors. This secondary stage of hemostasis will stabilize the loose platelet plug formed in primary hemostasis. This is a preview of the three pathways of secondary hemostasis. We will look at each pathway individually, starting with the extrinsic pathway. We're going to start with the simplest pathway of our coagulation cascade, and that's going to be our extrinsic pathway. Okay, so we are going to use a simple drawing of a blood vessel to really explain what I think is the most difficult part about understanding the coagulation cascade, and that is what are the triggers that activate the different pathways. As you can see, all we need is a capital C and a few lines, and this will represent any of our vessels. It could be a capillary, a vein, an artery. All our vessels can be represented by this diagram. And regardless of what type of vessel it is, it's going to have three layers, okay? Right here, the innermost layer that interacts with the blood, so the inside of the vessel, is going to be called the intima. And it's the part that is most intimate with blood. The outside layer that interacts with tissue is going to be called the adventitia. And then the layer between the intima and the adventitia is going to be called the media. So media, middle, intima, intimate, so the closest to, and the adventitia is the outside. Now, the only other part of a blood vessel that I think would be useful in helping us understand the triggers for these pathways is going to be that innermost layer of the intima, okay? So that's called the endothelial layer. And it's just a thin layer of cells that helps to regulate what goes into and out of the blood. So specifically for the discussion of the extrinsic pathway, we need to add one more thing. So we're going to add some membrane proteins right here. We know that cell membranes are filled with membrane proteins that serve various purposes. For this, for the extrinsic pathway, we're going to focus on what is called tissue factor. So tissue factor is a transmembrane protein. It is also called factor 3. So we'll be dealing with a lot of clotting factors in the coagulation cascade. So for the extrinsic factor, we're looking at, extrinsic pathway, we're looking at the tissue factor or factor 3. Now, tissue factor does not make contact with the intima layer. It runs through the adventitia and the media, but the endothelial layer keeps it away from blood. So it never makes contact with blood. Now within the blood itself, we have another factor called factor 7. So factor 7 and tissue factor, they never interact with an otherwise healthy patient. In the extrinsic pathway, if there is damage sufficient to the blood vessel, that tissue factor becomes exposed to blood and makes contact with factor 7. This is what is going to activate our extrinsic pathway to get the ball rolling on secondary hemostasis. And so the extrinsic pathway is really as simple as that. We're going to have, the extrinsic pathway becomes activated when you have some kind of trauma that is sufficient to make tissue factor enter the blood, make contact with the blood. There, it is going to form a complex with factor 7 and also with calcium. Calcium is an iron that we'll see a lot in the coagulation cascade that is required for activation of some clotting factors. So in tissue factor, factor 7 and calcium bind together. This is what is going to activate the extrinsic pathway, which will then go on to activate the common pathway via factor 10.
Now let's take a look at the intrinsic pathway.
Okay, so we're going to look now at the intrinsic pathway. Now the intrinsic pathway is a bit more complicated than the extrinsic pathway, but if you understand what exactly is happening and where all these clotting factors are coming from, it makes it easier to remember it and understand it rather than just memorizing the clotting factors. So again, we're just going to start with our big C and a few lines, and we're going to use that to represent our vessel. So in the extrinsic pathway, we talked about the adventitia layer and the media, so the outermost layer and the middle layer, and how there was tissue factor present there. For the intrinsic pathway, what we're going to focus on is that intima layer, right? And we talked about that intima layer having an endothelial layer, which is a small layer of cells that lines the intima. Okay, now right below that in the intima, there is a lot of connective tissue. A lot of connective tissue. So we're going to represent the connective tissue as these blue lines, and collagen is prevalent there. Now we have collagen in the subendothelial layer, subendothelial, so beneath the endothelial layer. And then in the blood, we have what is called high molecular weight kininogens. So we're going to do high molecular weight kininogens, HMWK. And those are found in the blood. So it's kind of the same situation. The collagen in the subendothelial cells, I'm going to put collagen right here, never makes contact with the high molecular weight kininogens. Now, if there is damage to the vascular sufficient that the collagen is now exposed to blood and makes contact with this high molecular weight kininogens, we get activation of the intrinsic pathway. Start. The complex formed by collagen and high molecular weight kininogens, this will go ahead and activate factor 12. Factor 12 will activate factor 11, which will then activate factor 9. Factor 9 will then form a complex with factor 8 in the blood, again together with calcium, and to this complex here will feed into the common pathway via factor 10. And there are a few tricks you can see here. If you have factor 12, it goes down to 11, then it switches up the Roman numerals to factor 9, and then you form your common pathway.
Now let's take a look at the common pathway.
So now we're going to look at the common pathway. And the whole point of the common pathway is that we want to generate these strong fibers called fibrin. And that fibrin is going to go back to our site of injury and reinforce that loose platelet plug that we created. That will give the body more time to hold that clot in place so it can heal the tissue around it without hemorrhaging out. So we already know that the intrinsic pathway and the extrinsic pathway are the routes of activation for the common pathway. They both feed into it. And they feed into it by activating factor 10, okay? Factor 10 is then going to activate factor 2. Now, factor 2 is very important because factor 2 is also known as thrombin. Now, our body has small amounts of thrombin that is circulating all the time. But the coagulation cascade amps up its production because it is thrombin that is going to catalyze the conversion of fibrinogen into fibrin, which is what we want. So when factor 2 gets activated, it is going to, let me grab a purple here, form a complex with factor 5, which is in the blood. And together factor 5 and factor 2 are going to activate factor 1. And factor 1, this is our fibrinogen. So the only thing left to do is to convert fibrinogen to fibrin. And to do that, factor 1 or fibrinogen is going to complex with factor 13 that is in the blood and calcium. And when those three things happen, we get the conversion of fibrinogen to fibrin that can make its way to our loose platelet plug and to help stabilize that plug and help the body to continue to heal.
I hope this helped to deepen your understanding of the coagulation cascade. It is usually a very complicated topic, but I really hope this helps. Head over to farmhercology.com for the complete study unit.